Hello everybody, today we're going to be looking at a tutorial on how to find the electron configuration, the noble gas configuration known as the shortcut, the orbital diagram for antimony, and I'm going to ask you how to find how many unpaired electrons there are, what block the element belongs to, and we are going to identify the 4 quantum numbers for the last electron. So first of all, if you look, antimony is element number 51. Okay, it is in the 5th period, and you'll notice it's right over here. This is where antimony is, number 51. So the first thing we're going to do is we're going to find the electron configuration for antimony, which has 51 electrons. Now, if you follow your sequence using the periodic table, the sequence goes like this. It's 1s2, 2s2, 2p6, 3s2, 3p6. Then you go to 4s2, followed by 3d10. Then afterwards you go to 4p6. Then you go 5s2, followed by 4d10. Now let's see here, we got, so far we got 10, 20, 30, 36, 37, 38, 48, and we want to get to 51, so the next one's going to be 5p3. So the electron configuration is going to be, as you see, it ends in 5p3. So that's the first question. Now, the second question is to identify the noble gas configuration for antimony. Now, if you notice, antimony is in period 5, and the noble gas of period 5 is xenon. Now, we're not going to use xenon. Instead, we're going to use the noble gas from the period above, which is from period 4, and that noble gas is krypton. Now, krypton is 36 electrons. So the first 36 electrons, rather than writing them as a full notation, what we're going to do is we're going to put a bracket, and we're going to put the symbol for krypton in that bracket, and that accounts for the first 36 electrons. Now, we do need to get all the way to 51. So after 36, if you continue following your periodic table, then it's 5s2, followed by 4d10, and then finalizing in 5p3. And if you notice, if you count, there's a total of 51 electrons here. You got your 36 from krypton, then 37, 38 with the S, 48 with the Ds, and then 5p3 will take you all the way to 51. Now, here's what we're going to do. The next step is to do an orbital diagram for antimony. And here, what we're going to use is arrows. Now, remember, the first one is 1s. Don't put the superscript. Instead, put a box and put one arrow going up and one arrow going down. Every time you write an S, you're going to draw one box. So the first one is 1s2, then 2s2. Now, it is important that you label your boxes. Label them underneath. After the 2s comes the 2p. Anytime you have a p orbital, you're going to have 3 boxes. And then use Hund's rule. So when I apply the 6, I go 1, 2, 3, and then you go back and pair them off, and that'll be 4, 5, and 6. Okay, then after 2p6 comes 3s2. Every time you're in an S, you draw one box. That'll be followed by 3p6, so again, draw 3 boxes. Use Hund's rule, 1, 2, 3, 4, 5, and 6. Then we go to 4s. Again, it'll be 1 box. And then afterwards, we're going to go to 3d. Now, every time you draw a d box, you're going to draw 5. And then the d is full, so you're going to put 1, 2, 3, 4, 5, and then pair them off 6, 7, 8, 9, and 10. Okay, so that'll be 3d10. And then afterwards, we're at back to P. It'll be 4p6. So you draw 3 boxes. Use Hund's rule and fill them in. Okay, and then now we're going to go to the 5s. Back to an S, so it'll be 2 boxes. Then it will be 4D. And for a 4, or for a D, I'm sorry, we're going to put 5 boxes again. Okay, if there was an F orbital, you would make 7 boxes. And then follow Hund's rule, fill them in. Just like that. Okay, and that one should be filled in right here. And then the final one, okay, right now, if you count, we have 48. The last one is 5p3. And this is the importance of Hund's rule, because when you use Hund's rule, you'll put 1 in each box. And you are now looking at the orbital diagram for antimony. Okay? Make sure you label your boxes, and you don't have to put superscripts. The arrows take place of the superscripts. Now, how many unpaired electrons are present? If you recall, the last box was a 5p3. So when you drew your orbital diagram and you used Hund's rule, you had 1 arrow in each box. Okay? So when you count how many arrows are unpaired, the answer is 3 unpaired electrons. So anytime you're asked to find unpaired, just do the orbital diagram for the very last one and identify how many arrows are unpaired. If a box is blank, that doesn't count. It has to be an arrow by itself in one of the boxes. Then the next question is, what block does the element belong to? And if you look at the block, you look at the very end, it ended in 5p3. And if you notice, all you got to do is identify what orbital it ends in. And this particular element is part of the P block. Okay, the P block is the area on the right side of the periodic table. It's groups 13 through 18. So this element, antimony, belongs to the P block. Now, here's what we're going to do. We're going to identify the 4 quantum numbers, okay, for the very last electron. The 4 quantum numbers consist of N, L, ML, and MS. So what I'm going to do to make this easier, let's put the 5p3 here, and let's put the 3 electrons, just like this. And the question asks to identify the 4 quantum numbers for the very last electron. So what you do is, the N value is the energy level. So this particular electron is in the 5th energy level. Okay? The second quantum number has to do with the orbital. If you are in an S orbital, the L value is 0. This element is in a P orbital, and the L value for a P orbital is a 1. Okay? Now, if you notice, let me erase this here, the ML value has to do with the orientation. See, the first box has a -1 value for ML, the middle box is 0, and the third box is +1. This particular electron lands on the third box, which has a +1 value. So that would be the ML value for this electron. And then finally, since the electron is pointing up, for MS, there's only 2 possible values. It's either +0.5 or -0.5. If it is pointing up, that means it's spinning clockwise, so you use the +0.5. Had it been pointing downwards, you would have put -0.5. Okay? And then finally, there is one more thing here that I'm going to add, even though it's not one of the questions. Let's say that antimony were to become +3. Okay, if you recall earlier, antimony has 51 electrons. So let me go ahead and rewrite this here. It's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, then you go to 4p6, 5s2. Okay, let me go here down here to finish this. Then you go 4d10 followed by 5p3. A plus 3 means that you lose 3 electrons. If it was negative, you're gaining electrons. So what happens is when antimony becomes an ion, it actually loses these 3 electrons. It no longer has 51, it now has 48 electrons. So you adjust the configuration and it would not have this last part here. In fact, let me write it over here. I'm going to go ahead and erase this part. And when you adjust and you remove those last 3 electrons, your answer to antimony as an ion would be what you see here. Okay? I hope this tutorial helps. With this, you'll be able to answer all those questions based on other elements that will be given to you.